and let me join all the other lecturers in welcoming you. In this case, I'm a bit late, so let me welcome you at least to the last week of the school. And let me also thank the organizers for putting together such an engaging and novel and creative online program. I think it's been very visible that we've all been enjoying this immensely. Now, they asked me to talk about amplitudes from the nodal sphere. And really, there's a word there that is implicit and that is really important, which is that what I'll be talking about is actually field theory amplitudes from the nodal sphere. Now, that's something that should be surprising and should cause you pause immediately. So you heard from, say, Ollie over the last few lectures that the sphere, at least, and higher genus Riemann surfaces play a really important role in string theory amplitudes. And what you've seen in this lecture is that you evaluate them, so you have an integral over the moduli space of the Riemann surface, so that would be mgn. And so the whole problem becomes a geometric problem. But on the other hand, if we look at field theory, certainly nothing of this survives. So from string theory, we recover the field theory amplitudes in the limit as alpha prime goes to 0. Now, if we look at this in more detail, what this really means is that so Q of t, we recover from string theory in a multifactorization limit, meaning we're actually looking at Mandelstam's alpha prime ki dot kj. So all of these go to 0 because we're sending alpha prime to 0. So there's a multifactorization limit here. And what this means is by the time we're in field theory, nothing is left of our Riemann surface. So in field theory, what we recover is just the standard Feynman diagram expansion. So very much a graph theoretic problem. And what you've heard about over the various lectures, in all of them basically, is how to solve or avoid exactly this graph theoretic problem. Now, a lot of modern amplitude techniques do manage to circumvent this to some degree. And in some sense, what we're going to talk about in this course really falls into that same area. So the question is there an expansion in a Riemann surface that reproduces field theory at each order? Now, there's a lot of things that would be going for this. So for example, note that in string theory, we have only one object at each order in perturbation theory, whereas here I've drawn this as one object, but really this is hiding an immense number of Feynman diagrams that go into each of these orders. It would be a massive simplification here. Now, let's say we wanted to go ahead and construct something like this. Where would you even start doing this? Now, one natural place to start is to start looking at the moduli space. After all, if we do want to end up with something that somehow lives on a sphere or in the end a nodal sphere, but in just any Riemann surface, then that is a very natural point to start. And if we want to be serious about this being a worldsheet method for field theory, then certainly in contrast to string theory, something that we would want is that we only look at the boundary of the moduli space say on the sphere when necessary, meaning when there's also a factorization in the kinematic space. So I've drawn a cartoon here of this. So on the left-hand side, we have some kinematic space just for 4 particles, n equals 4. You've seen I've been implicitly here using already that we're going to be talking only about massless field theories in this part. And I've used the standard convention. So my S is just K1 plus K2 square. And just because standard conventions actually are not standard, let me tell you that my T will be K1 plus K4 squared. And on the other side of this correspondence, oh, well, there's no correspondence yet, but on the other side of my sheet, I have drawn schematically the moduli space of a marked Riemann sphere with 4 points, and I've included the boundaries. So this will be the Deligne-Mumford compactification, but for our purposes right now, really the only thing that you need to know is that I've added all of these singular configurations here where our single Riemann sphere with 4 marked points splits up into 2, and always in such a way that there will be 2 marked punctures in each of these spheres. Okay, so our question then, if we want to move to the boundary of the moduli space only when necessary, is really, is there a map that interpolates between these two? And let me be very specific of what I mean by this. What we want is that we can start out here at a generic point, or start over here at a generic configuration, and that the two will be related. And also that we, and in particular, that we can start at a very special point in kinematic space at a singular configuration, something like s equals 0 up here, or t equals 0, or u equals 0. And this will have to be, apologies, and this will have to be related to the corresponding configurations here on the boundary of the moduli space. Now, the claim that we're going to make, and that we're also going to check in a simple case directly now, and the rest is something that you will also see in your homework, is that this is achieved by the scattering equations. And this is just a set of constraints, scattering equations. So I'll often write these as SE. Now, what could these be? My label I is going to run from 1 up to n. And these constraints E are just going to, well, they can only depend on 2 things. They can only depend on the Mandelstams and on the marked points on the sphere. So if you look at this long enough, something very natural to start out with is the dot product ki dot kj, and we will divide this by sigma I minus sigma j, where j runs here from 1 to n, but not equal to I. Sorry, I don't know if you can see this bit. Let me rewrite this. Okay. Sorry about that. And on that note, I will always use this sigma ij notation that says sigma I minus sigma j. Okay, so I'm claiming this right now, but really we should see that this is true. And just reproducing this as a cartoon here, let's look at this in more detail just for 4 particles. So where my cartoon actually holds. And in particular, let's look at the case. So the generic case should be clear. So if we plug in just some ki dot kj, some Mandelstams, we can solve this for the sigmas. And we'll get several solutions, but they will be generic. And the opposite is also something that you can easily check. So the interesting case is whether this really reproduces the boundaries. And without anything special, we can just look in particular at what happens as s goes to 0 and see whether this relates at all with the configuration where the marked points 1 and 2 sit on one side and 3 and 4 on the other. Now on the moduli space, we'll often parameterize this by sigma 1 is sigma 2 plus some small parameter epsilon, where would be explicit epsilon is much smaller than 1. Okay, so to see this, let's just look at, well, let's first do it this way around. So we'll split this into 2 parts of the proof. In this case, let's look at what the scattering equations look like when we use this parametrization for the marked points. In that case, close to the boundary of the moduli space, we just find that there's a term as 1 over epsilon that comes from the k1.k2 term. And then there's terms that are of order 1. So they look like k1.k3 over sigma 1, 3 plus k1.k4 over sigma 1, 4. And similarly for the scattering equation E2, but the only difference is now we have a minus sign here, and everywhere else we have to replace 1 by 2. I'm really just using the definition of these equations right now, nothing else. Now, if you look at this, you can see that there's this very simple manipulation that we can do, which is we can look at what the combination epsilon E1 minus E2 is. Now, on the one hand side, it's clear that this is 0 because the whole map is imposing that these constraints hold. So because E1 and E2 are 0, clearly this is also 0. On the other hand, you can just look at the explicit form here and find that this is k1.k2, which is s up to a factor of 2, plus epsilon times something that we won't particularly need to know. The only thing we need to know about f is that it's of order 1. So it's not of order 1 over epsilon or something. Okay, so we've seen that on the boundary limit, as we approach this boundary of the moduli space, where the approach is governed by the small parameter epsilon here, the scattering equations do indeed tell us that s goes to 0. And in fact, we know that s goes to 0 at the same rate as epsilon. Now, the other way around is equally simple. We can just notice that if s goes to 0, we can write both equations for 1 and 2. Let me call this I for the time being, as T1 over sigma I3 minus 1 over sigma I4, plus terms that will be of order S for I equals 1 and 2. And again, from this, we can immediately conclude that sigma 1 has to be indeed sigma 2 plus something that is of order S. So we can identify again the epsilon that parameterizes the boundary of the moduli space with S in the degeneration. Okay, so that solves it for 4 points. In general, something similar will work. And we won't go through it in great detail here, but it's very instructive. So you will actually do part of this on your homework assignment. And what you'll see is that you'll look at the moduli, at the boundary of the moduli space where I points on one side and some other number of points on the other side, and that the scattering equations relate this to singular kinematic configurations. So let me draw this suggestively as something that looks like a factorization limit in an amplitude. So S, and here we're looking at ki squared to 0. Now the idea here is going to be very similar. So you're again going to look at combinations of the scattering equations that mimic this behavior. Okay, now there's 2 more things that I would like to tell you about the scattering equations. Now, the most important thing we've already seen, which is that by construction, essentially, they encode the pole structure of massless field theories. That's certainly how I motivated them right now. And that is that will be for us the crucial feature throughout this. However, there's two more important properties that I've implicitly used in the above. One is that they're actually Möbius invariant, meaning invariant under effectively the action of the Möbius group on the sphere, which means immediately that only n-3 of the scattering equation of the n scattering equations EI are independent. Now, you can also look at how many solutions there are and what the solutions are like. And something that is very easy to prove is that the number of solutions is just given by n-3 factorial. Now, in practice, we will actually never solve these except for at 4 points if you want to be especially ambitious and do it on the homework. But this is something, that the number of solutions is n-3 factorial is something that's just a really short calculation. So it's not on the homework, but it's a good exercise to check this. And there's, in principle, two ways how you could go about proving this. One is there is a polynomial form that you can bring them into that is actually quite complicated and more involved. But a two-line proof is just to set up a soft recursion for them. And you will immediately be able to prove by induction, also given the 4-point example, that the number of solutions is then n-3 factorial. Okay, so we've seen that there are these constrained equations that we've called the scattering equations that map between kinematic space and the boundary and the moduli space of marked Riemann spheres. So that just means Riemann spheres with some additional punctures that I've labeled here. Now, what we're going to do for the rest of the lecture today is we're going to see how this actually combines into a full amplitude. Because of course, at this point, we're not there yet. We've done an important piece, but seeing how that comes out is going to occupy us for the rest of my 45 minutes in lecture 1. And what we're going to arrive at is something that is called the CHY representation of the amplitude. Now, in lecture 2, we'll actually see where these come from and develop the underlying worldsheet model. This is often called the ambitwistor string. And in lecture 2, really, we won't be able to get to anything new. We won't calculate any new amplitudes, but it's important to set this up because without a worldsheet model, there's no way we can even guess the amplitude at one loop. Remember, tree level is easy-ish. One loop is not easy, and anything higher is certainly hard. So there's no way we're gonna guess an amplitude coming from the torus. Now, that is what we'll do in lecture 3, and then I've marked it 4, but also in lecture 3 still, we're hopefully going to be able to see that for field theory, something magical happens, and you don't actually need the full contribution from the torus, but instead the full field theory amplitude actually comes from just the boundary of the moduli space of the torus, where the torus pinches, one of the cycles pinches, and you just find a nodal sphere of this type. And then hopefully we're going to have the full lecture 4 left to talk about what amplitudes on these nodal spheres actually look like and some important aspects of these representations. Okay, with that said, let me dive straight in. And let's have a look at what amplitudes from the sphere actually look like. Now, given that we found the scattering equations and that we know that how they relate singular kinematic configurations to the boundary of the moduli space, clearly we want to build our amplitude structure around that. And so you sit and you tinker and you think a bit, and if you're smart, so let me say that this is called the CHY representational formula, named after Cachasso, He, and Yuan. then the following should be clear. So we should write our amplitude at n points. My cartoon only contains 4. So we said we want this to be something that mimics, if you want, the structures of string theory. So we have an integral over the moduli space at n marked points here, and I've specified genus 0 because we're firmly on the sphere right now. We're not ready to move beyond that. And then the measure that we should write is clearly the measure that is appropriate for this moduli space, which is going to look as follows. We're going to integrate over all, sorry, this is an n, over all n marked points up to Möbius invariance. This is the quotient here is just the standard Faddeev-Popov quotient, but you'll also see this in more detail in the homework of how to actually calculate this. Then next, we know we actually shouldn't integrate because we have to impose, or at least not everything, we have to impose the scattering equations. That's, after all, what we said governs our correspondence between the kinematic configurations for massless field theory. So we should also impose the scattering equations, but remember, only n-3 of them were independent, so I'm going to mark this here with a prime. And we're going to impose all of these. Now, two things, maybe first. So we said the delta prime corresponds to only n-3 independent equations. And so there will be a Jacobian from which ones you pick. And it turns out that the Jacobian is particularly simple and is just the same as the SL2C Jacobian that you would find from usual Möbius invariance. So in particular, you will see that this becomes, I'm just going to write this in, if you don't impose equations 1, 2, and 3, then this will be just j equals 4 to n delta bar j. Now, the part that I didn't write yet is I didn't tell you what these delta bars are. These will appear everywhere. And these are just a holomorphic equivalent of the delta function. And they're defined by delta bar of z is d bar 1 over 2 pi I z. And you'll see on the problem sheet, on the very first exercise, you're going to be asked to show that this is indeed a good holomorphic equivalent of the delta function. Why do we need holomorphic? Because everything we've written right now is only holomorphic. Okay, so then often I will write this bit here, the bit that we've constructed right now, as d mu n chy, as the chy measure at endpoints, just to keep things brief. But remember, this involves the scattering equations here. Now we're missing something, and it's obvious that we're missing something by any measure, because right now, well, this is not SL2C invariant, we have the wrong weights everywhere. And also everything we said right now actually holds for any massless field theory. So in particular, this measure d mu chy is actually universal, as we've argued, meaning any massless, I'm going to not write this, but we will only be talking about massless field theories. So what we're missing, let me just call this IN, it's often called the integrand, and it's going to depend on everything. It's going to depend on the sigmas, it's going to depend on the momenta, and then it's going to also depend on any other data that we have in our theory. So let me just write this as epsilon here for the polarization, but for other theories, this could also be color structure, and we'll see this in a minute. So this is what is called the integrand, and in all theories that we're going to talk about, this splits into a left representation and a right, where all of these are, these are usually called half integrands for obvious reasons. Now, important is, this is actually where all the theory dependence comes in. So this is the part that tells us which theory we're actually looking at. And the other bit that is important is that by construction, we want this IN to only depend polynomially on the kinematic data. Why? We engineered the whole thing so that all the poles come from the Riemann sphere, from the punctures of the Riemann sphere. That was the whole point of the scattering equations, provided a map from the moduli space to the kinematic space. So this is only really meaningful that we can do this if we can require the integrand to be polynomial. Okay, so let me just make one quick observation and then tell you one important detail. So the first important observation is that you can just count how many integration variables you have right now and how many constraints you're integrating against. And if you check this, you can see that we're integrating over, well, n variables modulo the SL2C. So we have n minus 3 integration variables. We're integrating it against a set of n minus 3 constraints. So actually what we've written is fully localized. And in particular, that means we could write the amplitude instead, if we wanted, as a sum over solutions to these scattering equations, with the integrand on top and the Jacobian of whatever from solving the scattering equations in the denominator. Now, the other comment I want to make briefly is that for all theories that we're going to discuss today, the form of these integrands will be particularly simple in cases where there's a high degree of symmetry. So really, this representation lives from the fact that IN is simple for theories that we're usually interested in, like Young-Mills and gravity. Okay, with that preamble, let me actually tell you what this integrand is for the theories that we're usually interested in. In this case, I'm gonna give it to you for the bi-line scalar because that naturally fits into the picture, and Young-Mills theory and gravity. So there's going to be, as we said, the integrand decomposes into these two building blocks or half integrands, and we're going to pick these from a set of building blocks, which are either going to be some color structure that I'm usually going to write Cn for color. And if you've seen something like the Park-Taylor factor before, this is actually something you could probably guess if you stared at this long enough. So on the top, so alpha 1, we have the standard trace factor, and then in the denominator, I'm going to put what is known as a Park-Taylor factor, which is just differences of sigma alpha 1 minus sigma alpha 2, then cyclic up to sigma alpha n minus sigma alpha 1. Now, sometimes I'm going to write this Park-Taylor factor just for conciseness as either alpha 1 up to alpha n with brackets around it. And if I'm feeling particularly lazy, I might just write alpha, just for you to see the notation once. Now, the other object that we're going to need is something that tells us, so this carries all the color information. And you can see that it has, if you've seen Park-Taylor amplitudes, I think Henrietta might have talked about it. This is a standard cyclic structure here that you should be familiar with. On the world sheet here, but at least it should look intuitively familiar. For the kinematic part, however, we need a genuinely new object. And let me first tell you what it is. It's going to be a Pfaffian of a matrix M, but not a full Pfaffian. I put a prime here, and prime should always tell you that I'm reducing by something. And in this case, we're going to define this as -1 to the I plus j over sigma ij. And the Pfaffian of M where I've removed rows and columns I and j. Now, let me first tell you, so we now know what I mean by a reduced Pfaffian, but the M object here is actually very important. And what the M does, what the M looks like is it looks like it's a block diagonal matrix. It's in fact a 2n by 2n matrix, A minus C, T, C, and B, where the entries are just given by ki dot kj over sigma ij, same with polarization data, epsilon I dot epsilon j over sigma ij, and then the C mix polarization vectors and your momenta k, epsilon I dot kj over sigma ij. With diagonal entries 0, and these diagonal entries in the off blocks are defined just as a minus the sum over the rest. Now, if you look at the A's in particular here, you can see that they are given by ki dot kj over sigma ij, which should remind you of the entries in the scattering equations. And that is precisely the reason that we can't have the full Pfaffian here, but instead have to work with this reduced Pfaffian, because it's very easy to check, and you should do so, that we have a kernel. And the kernel is spanned by two vectors, one that just contains ones in the first n entries and then zeros, and one that just contains the sigma 1 up to sigma n in the first entries and then zeros. So this is true on the support of the scattering equations. The first one you can check directly. On the A's, this is just the statement that the scattering equations hold. And on the C's, you can see that they're designed so that this also holds. Now, why should this be a natural object to look at? Well, first of all, it has the correct dimensions in like mass dimension. It has the correct data. It's dependent on both the momenta and the polarization data. But one important thing that you should check is that it's actually gauge invariant. So in particular, if you replace epsilon by the momentum k here, that the whole Pfaffian reduced Pfaffian indeed vanishes. Okay, with these ingredients, then let me tell you, we have what the integrands are for the bi-adjoint scalar, Young-Mills, and gravity. So let me just sure I have enough space here. So what we see, what it turns out to be true, is that for the bi-adjoint scalar, we find two such color factors, Cn and C tilde n, which is not surprising because this is, after all, what we mean by bi-adjoint scalar, that it transforms in the adjoint of two color representations. For Young-Mills, we find one copy of this color factor, and the other copy is a reduced Pfaffian. Whereas for gravity, we find that we need two copies of these Pfaffians here. Whereby M tilde here, I just mean that you don't need to have the same polarization data. So you're free to replace all the epsilons that appear here by some epsilon tilde. Now, you've seen something like this already since Henrietta's lectures, and this should very much remind you of a double copy. In fact, I've very explicitly color-coded this to match the double copy relations. Now, as you can see, this is if you want a double copy on the worldsheet, and in particular at Line 0 right now, so on the sphere. But we can actually see that you can make this very precise and that it has a relation to the standard double copy that you've also seen now in Donald's lectures. And if you want to see this in detail, this goes as follows. Instead of the basis that we've been writing the color factor in, remember the color factor that we've written was in this trace basis. Instead of that, we can write alternatively the color factor using some standard identities as a sum over a KK basis, where by KK or half ladder basis, I really just mean, this is the image that you should have in mind. So we can fix the endpoints 1 and n, and the sum just now runs over permutations of these other legs of my half ladder. And at each of these vertices, we pick up just a factor of f a1 alpha 2b. That gives us a color factor in this basis here. Let me actually spell this out explicitly, 1 alpha n over the Park-Taylor factor that I warned you I was going to be lazy and just write this in this bracket notation as 1 alpha n. And maybe just to be precise, what we mean by this one here is the sum over b1 up to bn minus 2 of f a1 a alpha 2 b1 up to f bn minus 2 alpha n minus 1, I didn't plan this well, and n, an. Okay, so this is hopefully something that you have seen before for the standard, for just an amplitude decomposition. And it turns out that it's very easy to prove this, that the two color representations are equivalent on the worldsheet as well. Now, the interesting bit is that you can do the same for the Pfaffian, and you can show that the Pfaffian prime M has a very similar decomposition into a KK basis. Sorry, let me denote this. This is my KK or half ladder. And the only thing that differs is that you won't find color factors, obviously, on top, but you will find some numerator factors, also depending on the order here, with the same Park-Taylor factors in the denominator. And it turns out that these are indeed directly the BCJ numerators. Now, this doesn't hold on the nose in this case. This only holds modulo the scattering equations EI, so only on the support of these scattering equations. Now, there's various ways how you can show this. You can, for example, show that these exist by a KLT construction. Also, factorization tells you that these have to exist, and you'll see some hints of why this has to be true on your homework. But there's also various concrete algorithms that you can use that are much more effective than either of the two methods that I just mentioned. Maybe just to briefly remind you, why do these have to be BCJ numerators? Now, if we follow through everything and write out our full amplitudes, this means that for Young-Mills, our amplitude will just now decompose into as n minus 2 C1 alpha n a n of 1 alpha n, where these are my partial amplitudes, or color ordered. Whereas for gravity, the Pfaffian guarantees, if you push this through and just pull out everything that doesn't depend on any worldsheet punctures, that you will find this relation with the same partial amplitudes here, and that is just the defining relation, if you want, for the BCJ numerators here. Okay, so much for exploring the double copy on the worldsheet and how it relates to the standard double copy. Let me just make a few more comments about other theories in these representations. We won't talk about these in any detail, but I've listed here some that are known, and we won't touch on these, but if I'm not talking about your favorite massless theory, just pick one here, and there is a CHY representation. If your favorite theory is not on the list here, then it might still have a nice CHY representation. And I might just not know it, but if there is a good chance that if it has enough symmetries, that you can find a nice representation for it. Now, last but not least, I've tried to motivate everything, but I really haven't given you a proof that this actually reproduces the amplitudes. And I won't, but that is something that you will do on the homework, at least to some extent. So obviously we will not go through excruciating details on the proof there, but there's basically going to be two tools that we'll be using. And the first one is the BCFW recursion relation. So this is going to be an inductive proof. And the second one is the correspondence between the scattering equations and singular kinematic configurations that we've talked about at the beginning of the lecture. Okay, this is all the random comments that I wanted to make for these theories. Moving forward, something very natural that you could want to ask is, how does this generalize? Can you write loop amplitudes from a torus? And the problem is really that maybe we're smart enough to construct something like this for tree-level amplitudes, or at least Freddie and friends, Freddie Cachasso and friends are. But remember, one loop is not easy, really not easy. So constructing something like this from scratch without knowing anything else is actually really hard. So a better question is there something that can help us do that? And that question is really, is there a model underlying these amplitudes? By model, I mean a worldsheet model that explains why these amplitudes exist at all. Now, if let's say we were about to construct something like this, where would we start? How would we go about this? And what I want to tell you for the next 5 minutes is exactly this: how to construct such a model. Now, the first thing that we can notice is that we found a universal measure, meaning a measure that seemed to hold for all massless field theories versus theory-dependent integrands. Now, what this means is that, or what this suggests at least, is that we should construct our worldsheet action as a term that I'm going to call bare for now, because it's going to be what gives us the measure, plus something else that I'm going to call matter, because it is going to determine what the theory is. Now, the other bits that we should notice is there were two important features that we saw, which were, once we found the scattering equations, and these scattering equations actually are holomorphic delta functions, and they fully localize the integrand. So these seem very unique features of this amplitude representation. So clearly, it's a good idea to start our construction here. Now, what this suggests is that we should really take another look at the scattering equations. Now, let me just remind you, pin them up here so that you can remember these were just ki dot kj over sigma ij. Now, if you stare at this for a little bit and you experiment, you can see that there's one very suggestive thing that you can do. You can start writing these instead as follows. Let's say we construct instead a one form P of sigma that is the sum from j equals 1 to n kj d sigma over sigma minus sigma j. It'll be clear in a moment why I want this to be a one form. Then just having constructed this, we can see that then the scattering equations just become the residues at the points sigma I of p squared. Now this is a really short calculation, you should check this, but it's hopefully intuitively clear that this holds. That means that we now have a geometric interpretation for this. The scattering equations tell us that p squared of sigma is 0 everywhere, meaning for all sigma on the sphere. Now, just maybe to elaborate on this last step a bit, remember that on the sphere, a one form has at least two poles. So if I construct p squared as just the meromorphic quadratic differential, just this thing square, note not wedge square, so this doesn't vanish immediately, then I'll have to end up with something that has at least n minus 4 poles. So notice just by definition, p squared of sigma has to have number of poles has to be larger or equal than 4 just by construction as a meromorphic quadratic differential. But our scattering equations tell us that it has indeed only n, but it tells us that n minus 3 of these are 0. So that concludes that indeed p squared is 0 everywhere. Okay, so that now gives us a much better basis from which to build our model. So remember, on the last slide, we said we want to construct a bare action and a meta action, and we'll focus first on the bare action. And what it should do is it should somehow encode all of these options about or things that we learned about the scattering equations. And now we can summarize them and know that it now should encode p squared equals 0, and hopefully at some point with p mu sum from I equals 1 to n ki mu d sigma over sigma minus sigma I. Okay, so I think this is a good time to pause. So I would like to thank you very much for your attention, and when we come back, we'll actually go ahead and construct this action.